Welcome back. We will continue our journey through the computer article in Wikipedia, and we'll just sort of dive right in. We're just going to start reading about the essential components. It starts off fairly generic, or not generic, but starts off fairly low level, like control units, ALU, stuff like that. It's probably something that, unless you deal with that kind of stuff specifically, you probably won't ever come into contact with, but it's good to know about. And as we start writing programs and certainly stepping through instructions and stuff like that, it helps to have an idea of how this stuff works, just so you can sort of visualize it in your head, and you'll see it for what it is, which is just a list of instructions that the computer is executing. And then once you sort of have like a conceptual understanding of that, jumping around in memory and control flow all sort of, you have a better idea of what's really going on. And again, just from my own perspective, allows me to visualize it in my brain in a much clearer way. So general purpose computer has four main components: the ALU, or arithmetic logic unit, the control unit, the memory, and any I/O devices. These parts are interconnected by buses, often made of groups of wires. So like a system bus would be one example. And if you want to read about buses, which is something that this article doesn't touch on a whole lot, you could certainly check out that link. So inside each of these parts are thousands to trillions of small electrical circuits, which can be turned off or on by means of an electronic switch. Each circuit represents a bit or binary digit of information, so that when the circuit is on, it represents a 1, and when it is off, it represents a 0. The circuits are arranged in logic gates so that one or more of the circuits may control the state of one or more of the other circuits. This whole sort of paragraph right here, I mean, you could read this article, read this article, read this article, and then read about logic gates, and you'd probably still be, I mean, again, unless you deal with that stuff or you get into electrical engineering, it's not something that you usually deal with, especially like logic gates and stuff. It's good to know that they exist and it's good to know what they do, but actual implementation and like physically dealing with them is something that, unless you're an electrical engineer or a really low level sort of engineer, you're just not going to deal with that stuff. The control unit, ALU, and registers are collectively known as the central processing unit, CPU. Early CPUs were composed of many separate components, but since the mid-70s, CPUs have typically been constructed on a single integrated circuit called a microprocessor. The control unit. The control unit manages the complete computer's various components. It reads and interprets or decodes the program instructions, transforming them into control signals, or electrical signals, if you will, that activate other parts of the computer. Control systems in advanced computers may change the order of execution of some instructions to improve performance. So, I mean, basically, you could write computer code, it gets translated into assembly machine code, fed into the processor, and then the control unit sees it and may say, well, I could do instruction 5 instead of 1, and, you know, it's gain some efficiency. So it's kind of like on-the-fly optimization by the hardware, I guess, is one way to put that. But obviously, that's not something that you're going to deal with. It's a closest thing you get to a free lunch with computers, I suppose. A key component common to all CPUs is the program counter, a special memory cell or register that keeps track of which location of memory the next instruction is to be read from. So in the previous video, when we were reading through the earlier stuff, we had read about the idea of having like instructions in memory along with the data that's manipulated. And if you have instructions in memory, the computer has to know where it's actually pulling instructions from at any given time. Otherwise, it just, you know, doesn't know where to get them. And that's exactly what the program counter does. And when you get into like some lower level programming, I mean, you manipulate the program counter with higher level languages as well, but you just don't do it directly. All that stuff's kind of taken care of for you. But you can push any value, any address, any memory address you want into the program counter, and then it's going to try and read the next instruction off that address. And if there's not an instruction there, then you're probably in a world of hurt. Which, you know, is how you get into trouble when you're messing around with cheat engine and manipulating assembly stuff, and then you push the wrong address in there, and then the program counter hits it. It's not a valid instruction, and then your game / application crashes. But again, that's something that we will tangibly deal with. The control system's function is as follows. Note that this is a simplified description, but it's good enough for our initial purposes. Read the code for the next instruction from the cell indicated by the program counter. Decode the code for the instruction into a set of commands or signals for each of the other systems. Increment the program counter so it points to the next instruction. Read whatever data the instruction requires from cells in memory or from an input device, such as the keyboard. The location of this required data is typically stored within the instruction code, so we'll get to that. Provide the necessary data to an ALU or register. If the instruction requires an ALU or specialized hardware to complete, instruct the hardware, the ALU, what have you, to perform that operation. Write the result from the ALU back to a memory location or to a register or even to an output device such as your monitor, and then it just jumps back to 1. And so you can kind of see this is kind of like one cycle, if you will, for your computer, and that's basically all it does. Or for the CPU, it's basically just all it does. Since the program counter is conceptually just another set of memory cells, it can be changed by calculations done in the ALU. For example, adding 100 to the program counter would cause the next instruction to be read from a place 100 locations further down the program. Instructions that modify the program counter are often known as jumps and allow for loops or control flow and conditional execution. Examples of control flow. The sequence of operations that the control unit goes through to process an instruction is in itself like a short computer program. In more complex designs, there's a smaller component called a microsequencer, which runs a microcode program that causes all of these events to happen. I leave that as an exercise to the viewer. If that's something that you want to read or check out, you can definitely do that. The ALU. The ALU is capable of performing 2 classes of operations, arithmetic and logic. The set of arithmetic, or arithmetic, if you will, operations that a particular ALU supports may be limited to addition and subtraction, or it might include multiplication, division, trigonometric functions such as sine, cosine, etc. Square roots, obviously. Some can only operate on whole numbers, whilst others use floating point numbers to represent reals. Any computer that is capable of performing the simplest of operations can be programmed to break down the more complex operations into simple steps that it can perform. Therefore, any computer can be programmed to perform any operation. It'll just take more time to do so if the ALU doesn't directly support it. An ALU may also compare numbers and return truth values, such as true or false, depending on whether it's equal to, greater, less than, so on and so forth. Logic operations involving Boolean logic and or exclusive or and not. These can be useful for creating complicated conditional statements and processing Boolean logic. Boolean logic, conditional statements, and these kind of things right here we'll see them on a higher level when we start fooling around with Python, but suffice to say that the software versions are extrapolations / layered on top of the hardware ALU implementation. So if you do a Boolean logic task in a program, does that filter all the way down to the ALU? Maybe. I have no way of knowing. It might, but again, we will conceptualize and make that more concrete once we start fooling around with that stuff. And superscalar computers, we could read about that. Or you can read about that. I happen to have actually checked that article out. It's kind of interesting. Graphics processors and computers with SIMD and MIMD features often contain ALUs that perform operations on vectors and matrices. So obviously what they're doing there, the implication or the implicit implication is that they're doing 3D processing, which is all vectors and matrices and stuff. So if you can optimize that on a hardware level, you can speed up processing of 3D models and projection and stuff like that, but we may get to that at some point. I'm not sure. Memory. Computer's memory can be viewed as a list of cells into which numbers can be placed or read. So you might envision it as just a huge Excel sheet that only has one column. Each cell has a numbered address and can store a single number. The computer can be instructed to put the number 123 into the cell numbered 1357, or to add the number that is in cell 1357 to the number that is in cell 2468 and put the answer into cell 1595. That's a pretty good representation of how memory management or how memory manipulation works. The information stored in memory may represent practically anything. Letters, numbers, even computer instructions can be placed into memory with ease. Since the CPU does not differentiate between different types of information, it is the software's responsibility to give significance to what the memory sees as nothing but a series of numbers. That's incredibly important and something that we'll deal with when we get into pretty much anything. I mean, as we move forward and we look at Python, we look at programming in general, we look at start fooling around with Cheat Engine, and we talk about maybe how games are developed and things like that. With all of that is stuff that I would like to talk about. Basically, what this is talking about is a type system, as far as it's implemented in the software or from a programming language perspective. And from an app, and we'll talk all about type systems, I have no doubt. But from an application perspective, you can just jam anything it wants into memory, and the CPU / the RAM, the memory, whatever, does not care, and it doesn't even understand what it is to the application. So if you can just shove stuff into memory, and then it just sits there, and then when it reads it out, it is the application's responsibility to assign some kind of meaning and to be able to read that information properly. And that's you start that implication there, or the implication of that is that you get into things like protocols, file formats, things like that. So if you imagine like a JPEG or a GIF image, like it's just, if you have one of those in memory, like it's just a series of it's just a block of data, and the CPU and the hardware components have no idea what that is, and it's up to the like a photo viewer or a web browser or something like that to be able to read that format in a predefined way. And then again, that all sort of grows out of the fact that the CPU and the hardware really have no understanding of that stuff, and there's no reason that they should. In almost all modern computers, each memory cell is set up to store binary numbers in groups of 8 bits, called a byte. And we'll talk all about the 8-bit, byte, kilobyte, stuff like that. Each byte is able to represent 256 different numbers, either from 0 to 255 or negative 128 to positive 127. We'll get into that distinction, but basically what they're talking about is signed versus unsigned, or unsigned versus signed. To store larger numbers, several consecutive bytes may be used, 2, 4, 8. When negative numbers are required, they're usually stored in 2's complement notation. We could definitely check that article, or you can check that article out if you want to see how that works. Other arrangements are possible, but are usually not seen out of specialized applications or historical contexts. A computer can store any kind of information in memory if it can be represented numerically. Modern computers have billions or even trillions of bytes of memory. It's all just numbers, is basically what they're saying. The CPU contains a special set of memory cells called registers that can be read or written to much more rapidly than the main memory area. The main memory area is essentially referring to the RAM that you have in your machine. So if you have like an extremely time-sensitive information or something, or time-sensitive process that you need to execute, you would preload all the information that process would need into registers, or something, or suggest to the computer that, hey, you should put this stuff in registers because I'm going to need fast access to it. And not that RAM is slow, but registers are just faster because they're baked right onto the CPU. There are typically, and some of those, if I may, and again, we'll talk about this a little bit more, but there are general purpose registers, and then there are like specific registers. So we talked about the program counter in the previous one, so the control unit. The program counter is a register, it's just not general purpose. So you don't just push random shit or random stuff into the program counter, because as we talked about, if it can't understand, it's going to interpret that as a memory address and try and read instructions from that. And bad things happen when you just push random stuff into the program counter. The CPU contains a special set of memory cells. We read that. There are typically between 2 and 100 registers depending on the type of CPU. Registers are used for the most frequently needed data items to avoid having to access main memory every time the data is needed. As data is constantly being worked on, reducing the need to access main memory, which is often slow compared to the ALU and control units, greatly increases the computer's speed. I know I just said that main memory is not slow, but it's all a relative term. Main memory is still relative to like what we think about is like how fast we can process things is still pretty damn fast. Relative to things that are actually on the CPU, like the ALU and stuff like that, it's slower. But again, it's all a relative thing. You're not going to, in practice, unless you're doing like low-level stuff, you're not going to worry about whether your data's in a register or not. Unless, writing physics simulations or something like that. Like, you're just going to be you're just going to move most of your stuff into or store all your stuff in RAM, and the computer's going to go get it, and it'll figure out like, hey, I need this piece of information 10 times in the next 15 things, and it'll just usually it takes care of a lot of that stuff for you. If it doesn't do it, then certainly the compilers and interpreters do have a best effort in regards to that stuff. Computer memory comes in two principal varieties: RAM and ROM. So random access memory is RAM, and read-only memory is ROM. RAM can be read and written to anytime the CPU commands it. That's a pretty funny way of putting it. Anytime the CPU commands it. But ROM is preloaded with data and software that never changes. Therefore, the CPU can only read from it. ROM is typically used to store the computer's initial startup instructions. So you might think of like a post. So like when you first turn on your computer, most people get like a BIOS screen and stuff like that. Usually a lot of that stuff is stored in like a ROM chip or something like that. In general, the contents of RAM are erased when the power to the computer is turned off, but ROM retains its data indefinitely. In a PC, the ROM contains a specialized program called the BIOS that orchestrates loading the computer's operating system from the hard disk into RAM whenever the computer is turned on or reset. In embedded computers, which frequently do not have disk drives, all of the required software may be stored in ROM. Software stored in ROM is often called firmware because it is notionally more like hardware than software in the sense that it almost never changes. Flash memory blurs this distinction as it retains its data when turned off, but is also rewritable. It is typically much slower than conventional ROM and RAM, however, so its use is often restricted to where speeds are not a concern. More sophisticated computers, in sophisticated computers, there may be one or more RAM cache memories, which are slower than registers but faster than memory. So you have this kind of hierarchy of like places that the CPU can get instructions or data from, and so registers are kind of at the top of that hierarchy. In the middle you have cache memory, and then at the other end, and then next you have main memory or RAM, and then even below that you probably have stuff like hard disks and stuff like that. Generally, computers with this sort of cache are designed to move frequently needed data into the cache automatically, often without the need for any intervention on the programmer's part. I guess that's probably another free lunch. So that's 2 free lunches. We'll talk, or we'll read next about I/O. And I/O is basically, before we jump into it, is probably the slowest thing. So if you have like a process that's like crunching numbers and stuff like that, but then it has to go do some kind of input-output, whether it's on like a monitor or a graphics display or hard disk or something like that, I/O is by far always going to be the slowest thing, and more often than not, it's where you're going to find bottlenecks. And I suppose it's worth mentioning that most CPUs consider I/O to be low priority just because it's slow. So like put another way, like if you have 100 processes running on your system, one of them, or 100 programs, and one of them's like, I need to do I/O, it's just the computer's going to go deal with those other 99 programs because it takes a while for the I/O to complete, and so that process wouldn't be able to continue without that data anyway, so there's no reason to keep feeding it the ability to do computations and stuff like that. I/O is the means by which a computer exchanges information with the outside world. Devices that provide I/O to the computer are called peripherals. On a typical personal computer, they include input devices like the keyboard and mouse, and output devices like your display/monitor and printer. Hard disk drives, floppy drives, optical disk are I/O devices. Networking is another form of I/O. We'll get to all of this in much greater detail, or we'll certainly deal with it in greater detail. I/O devices are often complex in their own right, with their own CPU and memory. For example, a GPU might contain 50 or more tiny components that perform the calculations necessary to display 3D graphics. Most computers have smaller computers or smaller processors that assist the main CPU in performing I/O. Again, I'm not sure that makes it completely clear what I/O is on a functional level, but that's more of like what is an I/O device, and basically it's just there's a plethora of examples there. So we'll jump into multitasking here a little bit, and this is kind of getting into the idea of like how do computers deal with multiple things or do multiple things at once. And more often than not, multitasking, it's not really doing more than one thing at once, it's really just doing it so fast that us mere mortals cannot see the difference. Whereas multiprocessing is actually starting to do multiple things in parallel. While a computer may be viewed as running one gigantic program stored in its main memory, in some systems it is necessary to give the appearance of running several programs simultaneously, like any modern desktop that's been sold since DOS was invented or Macintosh was released. Like any consumer grade desktop device has to be able to do more than one thing at once, or at least fake it to where we can't notice. This is achieved by multitasking, i.e. having the computer switch rapidly between running each program in turn. One means by which this is done is with a special signal called an interrupt, which we'll probably deal with, we'll deal with at some point. So when we do deal with it, we're going to wind up reading this article, but if you want to jump ahead, you can certainly do that. So a special signal called an interrupt, which can periodically cause the computer to stop executing instructions where it was and do something else instead. By remembering where it was executing prior to the interrupt, the computer can return to that task later. If several programs are running at the same time, then the interrupt generator might be causing several hundred interrupts per second, causing a program switch each time. Since modern computers typically execute instructions several orders of magnitude faster than human perception, it may appear that many programs are running at the same time, even though only one is ever executing in any given instant. This method of multitasking is sometimes termed time sharing, since each program is allocated a slice of time in turn. You might have also heard the phrase quanta or quantum. That means the same sort of thing that we just read. Before the era of cheap computers, the principal use of multitasking was to allow many people to share the same computer. So you can imagine like an old 1970s mainframe with terminals and stuff scattered around an academic area, and then people are basically using the different terminals to interact with the same machine. And that's kind of where this whole like time sharing idea came from, or grew out of. Seemingly, multitasking would cause a computer that is switching between several programs to run more slowly, in direct proportion to the number of programs it is running. But most programs spend much of their time waiting for slow I/O devices to complete their tasks. If a program is waiting for a user to click on the mouse or press a key on the keyboard, it will not take a time slice until the event it is waiting for has occurred. This frees up time for other programs to execute so that many programs may be run simultaneously without unacceptable speed loss. We pretty much just talked about that, and when you're get into programming and stuff, you learn to kind of like, I don't want to say don't do I/O, but just that becomes it becomes highly relevant and necessary to understand when you start writing code and developing a program or application, whatever. You just have to treat I/O kind of differently, and maybe come up with ways to avoid it, or streamline it, or just there's multiple ways of dealing with it, and we'll get into all that stuff. Multiprocessing. Some computers are designed to distribute their work across several CPUs in a multiprocessing configuration, a technique once only employed in large and powerful machines such as supercomputers, mainframes, and servers. Multiprocessor and multi-core personal and laptop computers are now widely available and are being increasingly used in lower-end markets as a result. Odds are, if you bought your computer in the last 4 years, 5 years, whatever, you probably have like a dual core or quad core processor. So you're probably dealing more with multiprocessing than you are from like a uniprocessor architecture. Supercomputers in particular often have highly unique architectures and differ significantly from the stored program architecture that we talked about and from general purpose computers. I'm not going to bother finishing that. You can definitely check it out if you want. Networking and the internet. So networking is a topic that is entirely different, or like, I don't want to say entirely different, but it is such a huge topic that we're going to read this blurb, and we're not really going to focus on networking until later down the road. And when we do, we'll talk about like packet switch networks and token ring and end-to-end and IP addresses and layer 2 and layer 3 and switches and routers and stuff like that. And when we do, it'll become immediately clear why you can't just cheat in your online game. Hopefully it's clear to you sooner than why that's not going to work, but certainly when you understand networking and like offloading of data and signaling and communications and stuff, like you fundamentally understand why that's never going to work. But moving on, computers have been used to coordinate information between multiple locations since the 50s. The U.S. military SAGE system was the first large-scale example of such a system, which has led to a number of special-purpose commercial systems such as Sabre. In the 70s, I highly recommend you read about SAGE. I read that article earlier, and it was pretty awesome. In the 1970s, computer engineers at research institutions throughout the U.S. began to link their computers together using telecommunications technology. The effort was funded by ARPA, which is now known as DARPA, but before that was ARPA, and then before that was DARPA, and then originally it was ARPA. I don't know, it's kind of a thing. Every 6 years they decide to go back to ARPA, and then 6 years later they go back to DARPA. I don't know. Anyway, funded by ARPA, and the computer network that resulted was called the Arpanet. The technologies that made the Arpanet possible spread and evolved and essentially transformed into the internet that we all know and love today. I highly recommend you read about DARPA and Arpanet, and maybe we'll do a video on that, because it's all fascinating. And DARPA is just this black box of crazy. I mean, it's not a black box per se, but the stuff that they do is mind-blowingly insane. And the contributions into part of the Department of Defense, I believe, and anyone who has any issue with, or anyone who has ever doubted that government funding of science and technology has a noticeable effect on the consumer sector and just like technology and innovation, needs to read about DARPA, needs to study the history of the internet and all the different stuff in like Xerox PARC and stuff like that. I mean, granted, I think that part of that was funded by like the NSF, I think. We'll read about Xerox PARC and fact check myself later, but anyway, there's a compelling case that's hidden in a link for DARPA and the ARPANET and sort of the historical context of that. I highly suggest checking it out. In time, the network spread beyond academic and military institutions and became known as the Internet. The emergence of networking involved a redefinition of the nature and boundaries of the computer. Operating systems and applications were modified to include the ability to define and access the resources of other computers on the network, such as peripheral devices, stored information, and the like, as extensions of the resources of an individual computer. Initially, these facilities were available primarily to people working in high tech, but in the 90s, the spread of applications like email and the World Wide Web, combined with the development of cheap, fast networking technologies like Ethernet and ADSL, saw computer networking become almost ubiquitous. I don't think I've even, does anyone even call it the World Wide Web anymore? I don't know. I don't, but whatever. In fact, the number of computers that are networking is growing phenomenally. A very large proportion of personal computers regularly connect to the internet to communicate and receive information. Wireless networking, often utilizing mobile phone networks, has meant networking is becoming increasingly ubiquitous, even in mobile computing environments. Again, networking is something that we will get to in a very substantial way. Let's see, computer architectures. I'm not going to focus too much on that. Suffice to say that quantum computing appears to be where the next frontier. So, not to say that it's going to make digital computers obsolete, but it does seem that quantum computers are possible, and that's where all this is going. Let's see, logic gates. We'll read a little bit about this. The ability to store and execute lists of instructions called programs makes computers extremely versatile, distinguishing them from calculators. The Church-Turing thesis, again, Alan Turing, this mathematical statement of this versatility. Any computer with a minimum capability is, in principle, capable of performing the same task that any other computer can perform. Therefore, any type of computer is able to perform the same task given enough time and storage capacity. We will deal with this again in much more detail. Let's see, misconceptions. This is fun. The billiard ball computer. You should definitely check that out. Let's see, future, AI, hardware, history of computing. We're going to stop this here and probably maybe either go in the direction of networking or pick something out of this whole kind of like table of contents down here that we'll deal with next.